In this presentation, I'm going to be talking about the modal decomposition of spacecraft relative motion in quasi-periodic orbits. This is work that I conducted with my advisor, Dr. Schaub, at the University of Colorado Boulder. Conceptually, this work is about taking the relative motion dynamics in the case of nearby, slowly varying, or quasi-periodic orbits and applying some transformations to obtain a dynamically similar system for which the motion can be decomposed into fundamental modes seen here. Some further analysis isolates which of these motions are persistently reflected by the true dynamics, and those motions are used to construct a desired trajectory in a linear fashion. In this presentation, I'll start with a motivation for this work and move on to some of the details of the approach we took. Then I'll discuss the example application of formation flying around an asteroid, present some results, and summarize what we learned. So let's get started. For Keplerian orbits, the close proximity spacecraft relative position and velocity can be described analytically in terms of the orbital parameters of one of the spacecraft, initial relative state conditions, and an independent variable, either time or an angle. The Quasi-Wiltshire relative motion solution is the most well-known demonstration of this, but there are others. The relatively simple dynamics enable engineers to plan rendezvous and relative motion in a straightforward way. An example is given in this figure on the right, which shows how the dynamics of Keplerian relative motion were used to devise a simple and regularly repeatable orbit rendezvous plan for the shuttle. And with the addition of a few perturbations, we can still retain some of the simplicity of formation design for the earlier case. A good example of this is the J2 invariant relative motion condition found by Schaub and Alfrand. Despite the disruptive effects of J2, we can still obtain relative motion around the Earth that is bounded and easy to work with for formation design. By contrast, in asteroid orbits and in some lunar orbits, we are likely to encounter more complexity and difficulty. When you add many large perturbative effects, the simplicity in relative motion analysis from prior situations seems lost, and all you can generally say is that the relative motion dynamics will have some linear time-varying form, the details of which depend on the perturbations and the choice of coordinates. It's difficult to derive analytic models that account for the combined and large effects of perturbations for long time spans. This figure on the right is from a past work modeling the effects of low degree and order gravity coefficients and cannonball solar radiation pressure. The true motion is given in orange, and a model derived as a first-order perturbative correction to Quasi-Wiltshire only captures the unstable relative motion accurately for about one orbit without model updates or reinitialization. Generally, at some point, things can get complex enough that it's better or necessary to use numerical tools to approach this problem instead of analytic models. So this brings us to two important questions about formation flying in highly perturbed environments. First, how do we do formation flying in this context? And second, are there any analogs to the design approach for relative motion or rendezvous in Keplerian orbits? When can we recover a degree of simplicity in design? Now we'll move on to the approach in this paper. First, note that in this paper we linearized the relative motion using quasi-non-singular orbit element differences instead of local rectilinear coordinates. The orbit element differences just have much better linearization properties. So to get the relative motion dynamics, we linearized the Gauss planetary equations about one of the spacecraft in a formation, and the 6x6 plant matrix we obtain has many terms. Only 3 components are given here as an example. And using the resulting equations, we wrote a general numerical linearization toolbox valid for any perturbed relative motion problem. Again, this work applies to cases where the spacecraft and the formation are in quasi-periodic or slowly varying orbits. This has a wide range of applicability. For such orbits, we can show that the relative motion dynamics are in this linear time-varying form with an almost periodic plant matrix. So we'll factor the plant matrix into a periodic term, A bar here, and the smaller deviations, delta A, that prevent it from being periodic. And as a result, we can obtain a dynamical system that is similar to X, this XU system here. It has a periodic plant matrix. This figure below is central to the paper, illustrating these two systems on the left side. The true dynamics in orbit element differences are in the X space. The procedure is as follows. First, we numerically generate the relative motion plant matrix via linearization about one of the spacecraft orbits. Then a Fourier fit of the components of the plant matrix extracts the periodic part. Using the periodic part as a plant matrix, we compute an STM and a monodromy matrix. This is used to obtain a constant plant matrix, lambda bar, in this new coordinate system ZU. The XU and ZU coordinates are related by a periodic transformation matrix, and we use the same transformation to derive a new system, the Z coordinates, that is dynamically equivalent to X. Thus, examining the resulting dynamic equations in Z coordinates, we've transformed the linear relative motion problem from a system in X with time-varying, almost periodic plant matrix to a system for which the plant matrix is almost constant, lambda bar, but subject to small oscillations, delta lambda. So modal analysis is performed in this ZU space, and it is relatively straightforward to examine the relationship between X and ZU by looking at how ZU relates to Z. So expanding on what I just said, we let Z be equal to ZU plus a deviation, where ZU here is constructed from some or all of the eigenspace of lambda bar. We can show that Z and ZU are similar for some time if for all the chosen eigenvalues and eigenvectors used to make ZU, the deviations from delta lambda do not significantly disrupt the flow of the dynamics. And if this is satisfied, we can approximate the motion in X by a transformation from ZU for some time span. Thus, ZU enables the motion in X to be decomposed modally as well. To determine which part of the eigenspace in ZU is insensitive to small matrix perturbations and error, we can perform the whole procedure outlined on the previous slide in subsequent intervals or periods, and note which modes persist despite the slow variation in the plant matrix from period to period. Our thought was that these modes would be the natural basis for useful relative motion because they don't characteristically change a great deal regardless of when you compute them. So the basic idea of relative motion guidance in this paper is to perform the modal decomposition and do some analysis on the resulting modal structures to see which are robust to small perturbations and modeling error. Again, our hypothesis was that such robust structures would be predicted no matter when you do the modal computations. Then you construct a desired trajectory from a superposition of the available and desired modes, assuming that persistent modes are found, and that's illustrated partly in this figure on the right. Then, since you've done all this analysis using a dynamical system that's only similar to your true dynamics, you will have to do occasional small corrective maneuvers to ensure that the spacecraft follows the desired motion. So this is an interesting approach because it isn't about mitigating the effects of perturbation. The shapes of the modes themselves are a consequence of the perturbed dynamics. And this yields a straightforward approach to relative motion or rendezvous design that is quite generalized, requiring only that spacecraft orbits are quasi-periodic or slowly varying, and perhaps a bit of luck that your analysis will yield a sufficient number of useful natural motions from which you can construct a desired trajectory. There are some additional details in the paper that I won't have time to discuss here, including thoughts on an impulsive control strategy and an example derivation of the time scale between these corrective maneuvers. So at this point, we're ready to move on to a high-fidelity example to test the arguments in this paper. The asteroid Ryugu was selected as the body of interest for these numerical results. In particular, we're interested in information design in quasi-periodic Terminator orbits. So for this, we choose orbit altitudes that ensure commensurability of the asteroid rotation period and the orbit period, represented by this equation for gamma, which is a ratio of the body rotation rate to the mean motion of the orbit. This constraint maximizes the periodicity of the relative motion plant matrix, but also provides regularly repeating Sun spacecraft surface configuration geometry, which could be useful for a science mission. Additionally, the orbits were chosen to be larger than a resonance radius condition, the lower condition in this equation for A, to avoid destabilization by the rotating gravity field, and smaller than an upper limit, the one on the right, to avoid escape due to solar gravity and radiation pressure perturbations. Lastly, the dynamics in this example were made as realistic as possible, with solar radiation pressure and solar gravity being modeled, but also a 12 by 12 gravity field for Ryugu. To find the Terminator orbits, we solve for periodic orbits in the augmented normalized Hill three-body problem given by these equations here. Note that this beta term is the only parameter of interest in these equations, representing the relative strength of SRP. To solve for the periodic orbits, we use a multiple shooting predictor-corrector algorithm, and the redimensionalized periodic orbit initial conditions yield these dotted black orbits in the figure on the right, which are a family of periodic Terminator orbits. Nonlinear effects of solar gravity and the gravity perturbations from the asteroid destroy the periodicity, so we get these blue curves, which are the result of a 20-orbit propagation with the high-fidelity model. But the motion is still highly regular, as you can see. So these orbits would be good candidates for the placement of one or more spacecraft. In the paper, we focus on the third orbit out. Here, the body rotates 3 times for every spacecraft orbit, so our gamma parameter is 3. Now we'll discuss the numerical results. First, note that we applied the modal decomposition to the J2 only problem. The algorithm predicts that for 2 spacecraft with only a right ascension difference, there will be no change in their relative motion. This is a well-known result of the axisymmetry of the J2 problem, and it's reproduced by our technique. Additionally, we find that generally the form of the transformation matrix between ZU and the orbit element differences is near identity, with only 2 components subject to large variations. One's on the diagonal, and small oscillatory variations in the other components, represented by this P epsilon matrix on the right. This removes some mystery about what the ZU coordinates represent. By the form of the transformation matrix, it's instructive to think of them as behaving quite a lot like another set of orbit element differences. So now back to Ryugu. We apply the modal decomposition to the selected orbit and compute the eigenvalues and eigenvectors of lambda bar and the resulting transformation between the XU and ZU spaces. We did the whole modal computation procedure on 3 subsequent orbits or intervals, and note that 4 of the eigenvalues and eigenvectors do not change significantly between intervals, but 2 of them do. So this can be seen by looking at how the eigenvalues move in this figure on the left, or looking at the values in the table on the right. We ignore the resulting part of the eigenspace that is not persistent and focus on the part that is. In particular, let's look at the mode resulting from the pair of eigenvalues with slightly positive real part. So here's the modal structure transformed into local coordinates so you can actually see what's happening. It's complex and differs greatly from anything you'd see with Closey-Wiltshire dynamics. It starts out with very little z motion, but then the relative orbit rotates out of plane and distorts over time. It also becomes thinner in the x direction, but it's bounded and well followed by the nonlinear dynamics. So multiple spacecraft could target different scalings or phase shifts of this modal structure and would remain in each other's vicinity for long time spans. So this is a well-behaved, bounded, and comprehensible structure that could be useful for formation design. And this slide gives some additional results. First, note that the modal predictions are given for 3 subsequent intervals in this figure on the right. It might be a bit hard to see without zooming in, but the same characteristic structure persists regardless of when you compute it. In addition, I thought it would be a good idea to plot a component of the plant matrix in the space of quasi-non-singular element differences and its Fourier fit on the first interval, given in dark blue. The light blue is that same Fourier fit applied to the subsequent interval. This figure basically shows, by one component, that the plant matrix is nearly periodic, and the Fourier fit changes only slowly over time. At this point, I'll summarize the results and findings. So first, this presents a new analytic perspective and new numerical tools for spacecraft relative motion guidance in close proximity in quasi-periodic orbits in highly perturbed environments. We do a transformation to a dynamically similar system for which the plant matrix is LTI. We do a modal analysis on this system, and the state error from that can be analyzed. In this work, the methods were tested on J2 dynamics and Terminator orbits about Ryugu, which gave some interesting results, including the robust relative motion modes that we found that change only slowly. So these would be suitable for a guidance strategy. I'd be happy to answer any questions about this work. Here's my email address and a link to our lab website. Thank you for your time.